Right. Well, hello, folks. Thank you for joining in. My name is Jimenez. I'm from the Microsoft Edge team, and I would like you to go down the rabbit hole of GridNG with me. I brought up this presentation to give you a hopefully brief, but really insightful intro to how we changed the CSS grid implementation in Layout NG. So, without much further ado, I would like to move now because we have a lot to cover. So let's just get right to it. I would like to go over a quick refresher of grid concepts so that everybody is on the same page. As you might already know, css-grid provides like a very easy way for web authors to position elements in a two-dimensional space, keeping the alignment between elements somewhat well-defined and with minimal effort from the author part. Grid layout is entirely based on dividing the space that you see on screen into rows and columns. And we can even specify how much any given space it's taken by those grids. These columns and rows. The most powerful tool that CSS Grid has is like the placement that we can give for this children element. We can specify which rows and columns a child element, also known as a grid item, should be aligned to with ease. And we can even let the auto placement decide where to place those items for us. Grid items themselves can be grids too. However, a nested grid establishes its own rows and columns by default. As you can see on the grid on the left, the nested grid has its own standalone grid lines that are not aligned to the dashed lines that we see on the background. And as any web developer might tell you, this is not always ideal, since we might want to keep the children of a nested grid aligned to the rest of the grid. So we have a very interesting feature coming up that it's a subgrid, and it's coming to solve this problem specifically. With it, we will be able to inherit the specified rows and columns from its parent without the need to redefine them. Now, in order to define the rows and columns of a grid, we need to talk about a track collection. A track collection establishes the divisions that we use to place grid items in a given dimension, and it is defined by the grid template columns and grid template rows properties. These divisions of the space we call grid lines. We can refer to those grid lines by a positive or negative integer, depending on which side of the specified repeater we want to address. And the space between those grid lines, it's called a track. Grid layout gives web developers like a lot of control in how do we size those tracks. We can specify like a fixed size, like in here, 50 pixels. We can specify to grow, to allocate the size of the grid items that are placed within them, or just to take a portion of the leftover space. Finally, I would like to go ahead with the concept that will take a lot of value in the next slides. Repeater. This is a neat feature that CSS Grid allows authors to specify a recurring set of track definitions that redundantly repeat a given number of times. So, in other words, it's a very compact way to express like a bigger pattern of tracks. Like we see here on screen, we basically want to repeat this set of tracks, 50 pixels auto and one fraction 3 times consecutively, and without much effort into actually writing them, all of them. Now, I would like to slow down a bit now that we have like the basics covered, and we will talk about what GridNG does differently from our legacy implementation. And there are 2 key features that we enforced that were like very deliberate in order to improve performance and memory usage. First, we wanted to avoid expanding repeaters. I will explain a little bit about this. We will dive more in upcoming slides, but let's just give a quick example. Let's assume that we want to lay out a grid that has like a column definition of repeat 1,000 auto tracks. So basically, that will be an empty grid that only will size the size of the grid items. In the legacy implementation, this will be each of the tracks will be created and sized, and as such, the grid sizing algorithm will need to perform more operations for every track. meaning that the performance will rely on the total track count specified by the author. In GridNG, we think that this is unnecessary. In order to perform layout, we just need to know the total size of a track collection. And in order to position the grid items, we just need to know like the logical position of those items. So like I said, I will go a little bit deeper into this, but the point that we want to make is that we want the complexity of this algorithm to be directly related to what the author actually specifies. If a web developer writes like this example, repeat 5 tracks of 10 pixels and just places 3 items, even if we change the track count to 1,000, laying out shouldn't be a surprise. Like this increase in the track count shouldn't be a surprise since the author didn't take much effort to change it. So the second feature will be, we want to keep the context of our methods in stack and pass them all around via parameters. The key to this decision is statelessness. This will resonate more later when we talk about the inherited advantages from layout in G. But a concrete example that I want to give, it's like before doing layout, we actually need to know the placement of every grid item in the grid. This is done by the very complex auto placement algorithm. And in the example that I'm putting here on the slide, we may have like the same grid items and the same repeater definition happening in both of them, but we want to trigger a relayout, let's say because the grid container changes its available size. We don't want to throw that up. We don't want the placement to be invalidated, and that's the place where its statelessness comes into play. We just want to invalidate this if the actual information that we have from placement changes from the one that we already had. And so let's go back a bit so that we can explain more about what we mean by zone expanded repeaters, because it is a very hard concept to grab. Let's start by thinking in a grid that has no grid items and we only have like a repeater specified. The key idea behind GridNG is that we don't actually need to create the tracks to size this repeater. We can just plug the number of repetitions into it. Like in our example here, we have like a definition of 5 pixels, 1 FR, and 5 pixels too. So we can just plug like the number of repetitions and know that this entire repeater will take 15 pixels, 3 fractions of the space, and another 15 pixels at the end. So that much is easy enough, but there's like the obvious problem of introducing grid items. Whenever we introduce this, we know their position in the grid after placement, but you may notice that the placement breaks kind of the repeater in 3 parts in this example that I give you. Like you can check that the repeater actually gets like broken in the start of the grid item and the end of the grid item. Our next key observation will be that those broken repeaters, we will see them out in the next slides, can be treated just as regular repeaters, but just like altering a little bit the specification. For example, let's see the left side that contains the start of the repeater from the start of the repeater to the start of the grid item. This little part over here, that can be treated taking the first track of the repeat and saying, I will just repeat that track 1 time. That is easy enough. Next, we will have to take a look at the actual span of the grid item that can be represented with the same track definitions as the original repeat, but with a different offset. Starting in a different offset from the original repeater. We will start in 1 FR, then have 5 pixels, and cycle back to the origin of the repeater. That will be again 5 pixels. And we can accomplish the entirety of the span by repeating this once. And next, taking a look at the end of the grid item to the end of the repeater, we can see that we can take, again, that same definition of the repeater, 1 FR, 5 pixels and 5 pixels, repeat it 2 times to complete the broken repeater. Now, if we use this definition as it is, it will be a size of 2 times 3 definition 6. So we need to clamp that definition of the repeater to 5 tracks so that we don't grow bigger than the actual repeater that we were trying to size. So knowing how those repeaters can be broken, now we want to introduce the concept of a track range that we basically use all of the start and end boundaries of both the repeaters and the grid items so that we can define ranges of tracks that are not broken into smaller repeaters by, like I said, either the boundaries of a repeater or the boundaries of a grid item. So then we can guarantee that every grid item that we specified can be perfectly sized using a continuous subset of track ranges. It is also important to notice that this number of track ranges in the grid is proportional to the number of the specified grid items and repeaters. If we have more grid items, we will have twice more track ranges. If we have more repeaters, we will have more track ranges. So that is exactly what we wanted when we established that we wanted the complexity to be directly tied to the author's specification and not to track count. One last thing, in order to treat those track ranges as repeaters, we actually need to know the track sizes it spans. In the example we had on screen that is different from the previous slides, we have a repeater, 5 times 50 pixels auto and WFR, broken into 3 ranges. You can see in the little line that it's drawn with the name ranges, it is broken into 3. Using some magic, using modulo operator, we can actually compute how many of those track definitions appear in each of the ranges. Like, for example, in the first one, we know that in this track range, we have 2 times the 50 pixels, 2 times the auto, and 1 time the 1FR. So this bit of data that it's enclosed in a circle, it's called a set of track definitions, or in the GridNG world, we just called it a set, simply a set. Each track range, it's associated with one of these, and they are used at layout time so that we can know how to size each bit of the track ranges. At the end, there's a very clear advantage for layout in G. Instead of allocating data for each specified track in a repeater, we only allocate data for each track range. The data that we want to store for that, we know in this example, the range takes every track from the first track up to the 3000 track. And we just need to know what are the sets that are contained in this span that are repeated like X number amount of times. So in here, we can notice that this range is equivalent to having 1,050 pixels, equivalent to 50,000 pixels total. The 1FR, it's accounted for with 1,000 fractional units. And the last one will be, we'll need to account for 1,000 auto tracks. Getting used to this concept takes a little bit of time. But in practice, the implementation of the grid algorithms in our code base, it's almost seamless. It really doesn't do anything very differently. We just need to wrap our minds around treating sets and plugging in the repetition number. So moving forward, let's take some time to see how the GridNG pipeline puts into practice everything that we have discussed so far. I will guide you all the way around. Grid placement is the first step in the grid pipeline. And in other words, we just want to resolve the cryptic placement properties of the grid items to get a set of definite positions of the grid. When I said cryptic, I just mean that the auto placement algorithm is super complex. And that's why we actually wanted to cache the result positions. We just discussed a little bit about that before, but just wanted to give a quick reminder. The next step, with the grid items, their position already resolved, and knowing the repeaters of the explicit grid, we want to build the track ranges that we already discussed for the grid. This happens entirely in the class ngGrid block track collection. And it is important to note that at this same point, we will cache some information regarding the grid items and the tracks it spans. This happens before, well, these properties are cached because they're going to be relevant in the next step, that it's going to be grid sizing. For example, we need to know the actual subset of track ranges that a grid item spans, and other useful information as if a grid item spans any intrinsic or flexible sizes. As I already said, the track sizing algorithm works basically the same. There's no really noticeable difference. You just need to keep the math on your head so that the repetition number is accounted for. And after that, it's worth mentioning that the grid sizing might need to be redone when the available block size is indefinite, because we may have a dependency on it. For example, we may have a row that is required to resolve with a percentage size or a flexible size, and whenever we have like now a definite block size, we need to recompute all of the grid. And finally, we have the actual layout step. And in order to know the position of each grid item, we will cache the start offset of every set, accounting for any align or justify properties. And these offsets are known as the grid geometry. This is the most important bit of data that we store in ng-grid layout data, that it's like a class that we pass around a lot because it contains all of the information we need. The grid geometry, it's actually something, well, with the grid geometry, we can basically build everything that we need for placement. We can determine the size of any subset of track ranges in order to build a constraint space for a grid item. We can determine the logical position of an item just by knowing the offset of the first set it spans. We can determine the final size of the grid just by knowing the end offset of the last set in the grid geometry. So it's very powerful. And it's also worth mentioning that at this point, for fragmentation, we do all of the necessary adjustments to that grid geometry so that we can have like fragmentation working. Now, it is important to know that thanks to this grid geometry, we can easily determine whether any grid items change its constraint space. And that's where we get like layout result caching for free. This is like an advantage that we have from layout-ng, and with how the constraint space invalidation works in mind, this is just basically like free real estate, right? The constraint space for a grid item, it's built from the layout data, and that layout data, whenever it changes, it will only invalidate the relevant grid items that are touching that, well, those changes. For example, in the slide here, let's say that a column changes from 50 pixels to 100 pixels. In this example, the grid item on the left, it's spanning the column that changes. And as a result, the constraint space that it is sized on might change, and that gets the layout result invalidated. But in the other case, around in the right side, we'll have like a grid item that does not get its constraint space altered by the changes on the ng-grid layout data. So we can simply reuse that for free. And so I would like to conclude this presentation with a quick summary of what's to come in GridNG. And of course, talking about that, we have like a very big elephant in the room, that it's Subgrid. And Subgrid will challenge a lot of implementation. I will give like a quick summary of what are the key points to talk about after. And hopefully we will talk about this in another presentation in maybe BlinkOn 17. Subgrid items are items that are, a subgrid specifies, but are delegated to the parent grid for sizing. Those subgrid items need to be placed before we actually size the parent grid. This is a problem because that basically states in the current state of our algorithm, basically the first step of layout, it's placing. This implies a circular dependency, where in order to have the placement, we actually need to call layout, but we cannot call layout because we need placement first. So we need to isolate grid placement from layout so that that happens independently. The next one will be that the subgrid effectively inherits the grid lines it spans within its parent. And there are two key points that makes this really difficult. The first one is that we need the actual grid geometry passed down to the subgrid. This is something that we will do by introducing the grid geometry to the constraint space. And the neat part about it is that once we do that, just as we discussed in the previous slide, by passing them to the constraint space and checking if the grid geometry is different, we can get layout result caching for free. The second part will be that also the grid line names of the grid need to be inherited to the subgrid. And that it's pretty complicated because the current state of grid positions resolver does not take into account this. And we will need to basically refactor all of it to introduce like a set of line names that are incremental that we can expand by going recursively into levels of subgrids. And the last but not least, it's that we need to take into account the margin border padding scroll bar size of a subgrid without sizing the subgrid. In other words, a subgrid is effectively considered empty for a parent grid. And that has the problem that how are we going to account for that MVP size if we are not actually sizing the subgrid? We need to have 2 points. First, we need to rework the track sizing algorithm to accommodate hypothetical items so that the actual size it's accounted by hypotheticals. And the other one is that we actually need to introduce accumulated extra margin to the subgrid items to lay them out correctly. Like I said, since the subgrid does not account for its margin border padding itself, you need a way to actually lay out the items correctly without that being plugged into the grid geometry. And basically, that's everything that I had to share today. I would like to give a very special shout out to all of my peers from the GridNG task force. They did a really good job to land GridNG at the state that it is in currently. We got it up and running basically with minimal regressions or number of things that we needed to fix at the end. A huge thanks, and thank you very much for joining in and listening. I don't know if we have a lot of time for questions because I'm mostly host all the time, so let's see. So what is the expected time here? Because probably it's a good time to call it for a break.
Yeah, if we don't have any questions, I think we can wrap it up and go for a quick break. Thanks, Ethan.
Sounds good. All right. Thank you, folks.